Today's webinar is on failure rate prediction using FMEDA and Exeter's FMEDAx tool. Exeter. Who's Exeter? Exeter is a global company with offices around the world. Our most recent location is Exeter, Ireland, but as you can see from the map, we're basically all over the world. You can find an Exeter office somewhere more or less near you. All of our methods and data are published for everyone's benefit. We feel being an open book and sharing in our knowledge only strengthens the marketplace. The faster we teach you and your colleagues, the faster our research team can begin working on the next safety initiative in improving our industry, making us all safer. Exeter is a company, customer-focused company. We're the only company that encompasses the complete life cycle of functional safety and cybersecurity. This makes us unique and allows us to bring a lot to the table. Well, the picture says it all. In 20 short years, we have emerged as the leader in safety device certifications, even in logic solvers. And in cybersecurity, we're even further along, which makes sense since all the organizations started at roughly the same time. Exida tools have become the most widely used globally in the industry. We thank all those who have given us feedback for improvements. We're constantly updating our tools based on the feedback received. And in today's webinar, we'll be talking about the OEMX suite of tools for you, the manufacturer. In today's webinar, we'll be discussing why we need failure data that's customized for the industrial automation space. How can we obtain that data? How can we predict data for our element or product using failure modes, effects, and diagnostic analysis? We're going to show Exeter's new FMEDAx tool, and we're going to go through an example of a simple type A enunciator device using our OEMX suite, which comprises ArcX and FMEDAx. Many industries need realistic failure rate information for many purposes. They want to know how their product is going to behave in the field. They want to know what their warranty costs are likely to be. And they want to meet functional safety standards, which require certain types of data and metrics to be presented to the end user. What kind of data do they need? Well, they need to predict the field failure rate for their operational profile. They need to know what ways their product is going to fail. They need to know if they implement automatic diagnostics, how much that is going to improve their product's performance. And they need to know when the product is going to begin to wear out, where that right side of the bathtub curve starts. So what is a failure rate? Well, bringing it down to the basics from the book, failure rate is failures per unit time and also per quantity exposed. That failure rate, the simple lambda of T, is the basis for many other common measures provided in reliability engineering calculations. Probability of dangerous failures per hour, average probability of failure on demand, safe failure fraction, risk reduction factor, spurious trip rate. In particular, IEC 61508 requires particular set of metrics to be delivered to the end user. The failure rates for what I call the 4 buckets. So there's dangerous failures, which are failures that make the product unable to perform its safety function. There are safe failures, which cause the product to perform its safety function even on lack of a demand. Each of those is subdivided into failures that are either undetected or detected by automatic diagnostics. 61508 also would like you to present proof test coverage numbers for an example proof test. In addition to all these, if you want to do more detailed modeling, it's useful to have failure rates for the diagnostics themselves, which we refer to as enunciation failures, and also failure rates for failures that do not affect the safety function. These are useful during surveillance audits where the overall failure rate of the product is compared to its predicted failure rate. Since the overall failure rate includes these no-effect failures, it's the number that should be compared to the actual failure rate during a surveillance audit or during your own analysis of field failures. Where do you get field failure data? Well, there's 2 fundamental ways of getting it, looking back or looking forward. Looking back, you can estimate lambda based on field failure data. You can use tools like Exeter SILSTAT or simply your own product history. The other way is looking forward. You can predict your failure rates either based on the test results of a small sample or by analysis using an industrial safety failure rate database. Let's try going back first. Failure rates can be estimated from field failure reports if the analyst has good uncensored failure reports with complete information. If the information is incomplete, assumptions must be made. And the assumptions can impact the result by orders of magnitude. We were once told by an engineering manager, I can hire a statistician to give me any answer I want. And that's true, but only by using bad assumptions. For instance, here's a manufacturer field return study. Field proven mean time between failure numbers are very high, which means the failure rates are very low. I think those of you who have experience in the field can see that a logic solver with a fiber optic network interface is not likely to have a mean time between failures measured in centuries. But that's what this database seems to show. Another problem with using backwards looking failure rate estimation techniques is obsolescence. You can only get data from field returns on a product, obviously, that's been fielded. By the time you get enough data, the product might be obsolete. So you can't really use this technique to get data on a new product or on a product that doesn't have a lot of field experience. So the other technique is failure rate prediction. There are a couple of ways of that, getting failure rates on products that either don't exist at all or only exist in small quantities. One way is to test a set of prototypes. One way of doing that is cycle testing. Now, those are only useful for your final application if your final application does something similar to the cycle test. For instance, you're not going to find out about something like cold welding or stiction by continuously moving your product. Another way of getting this data is by doing a part stress analysis based on a component database that predicts the total failure rates. Essentially, you're doing object-oriented design on your hardware. The FMEDA, Failure Modes, Effects, and Diagnostic Analysis, is a predictive technique based on design strength analysis. It uses a component database that should account for design strength versus a predefined environment, and it should present the failure modes, diagnostic coverage, and useful life appropriate to the actual use environment. The classic database for part stress analysis is the Mill Handbook 217, A through F. It's been out for decades, and there are two methods. There's a parts count method, which is easy. You just add the failure rates of the parts from data tables and you get a total number. And then there's a part stress method that adjusts the lambdas for specific environments, such as ground fixed or airborne mobile, to get theoretically more accurate failure rates. One of the problems with the military handbook numbers is they tend to be quite pessimistic, 4 times to 20 times what you will expect to actually see in the field. If we look at the same set of products that we looked at field failure studies for earlier, and we compute the Mill Handbook 217 F numbers, you can see that they are much more pessimistic than the field failure numbers. Again, if you had a logic solver with a fiber optic network interface, I think it's safe to say that you would expect to see a lot less than 1 failure per year from a population of 15. Right? So we're looking at almost 12 to 1 ratio, and the reality is probably somewhere in between. Engineers at Exeter created the FMEDA method by combining techniques from reliability engineering, Mill Handbook 217, failure modes and effects and analysis, diagnostic analysis. Components from a design are chosen with an operational profile, which is in turn chosen from common operational profiles from the industrial space. Failure rates and failure mode distributions are then provided from a database, and if diagnostics are in place, those are chosen as well. Those all get added up at the subsystem and finally at the product level to provide the failure rates and modes and diagnostic coverage and other IEC 61508 required metrics for the product. The FMEDA method was specifically created to allow practical implementation of functional safety compliant products. So as I said earlier, the FMEDA is essentially object-oriented design applied to hardware, where it works extremely well. An FMEDA is a systemic, detailed review of that design, resulting in failure data prediction. However, you have to have the right data coming in, or you can't get the right data going out, as we all know from experience. How do we overcome this problem? Well, you can combine estimation and prediction in order to get a database of failure rates that are vetted at the industry level. So Exeter has created what we call the calibrated FMEDA. To produce realistic results, the component database is calibrated with field failure data from end results in a similar environment. We obtain those during our surveillance audits of certified products. For electronic components, the failure rates have been derived starting from the original IEC Technical Report 62380 models, among other places. Exida added a term in the equations from Siemens norm 29500 to 62380 for analog ICs. We also added new failure modes and failure mode distributions from research and field failure data analysis. We added useful life imitations per component manufacturer data and research. We've extended some parameters from IEC Technical Report 62380 for electronic components during comparisons with field failure data and root cause analysis of actual device failures. We've got over 400 billion unit operating hours of equipment data we can use to compare with our database. We've also added soft error or single event upset failure rates to semiconductors based on research papers and semiconductor manufacturer data. For mechanical and sensor components, failure rates have been derived from field failure data collection and comparison with the cooperation of mechanical device manufacturers. Again, we've got a lot of operating hours of equipment data from multiple applications and operating environments. When we have data for both static and dynamic applications, that's important. So how do you access that database? Well, we think you should do it using the Exida FMEDAx tool, because that includes our calibrated component databases for electronic components, mechanical components, and sensor components. It also provides you with the mechanisms to take that database and use it to build up an FMEDA, which will give you the metrics you need to present to your end users. So let's use FMEDAx for a demonstration product. Here's the product. It says, and this is what marketing has delivered to we the engineers, our existing annunciator uses relay logic and incandescent lights. We'd like to reuse the existing mechanical design, but we'd like to have LEDs inside, and we'd like to get rid of the relays. We've got a laundry list of requirements here. We want redundant power inputs, 24 volts nominal, protected from transients and overvoltage. We've got a limit on our power consumption. We want it to flash about once per second, like our existing unit. We have a minimum requirement of light output. We want a diagnostic output that lets us know when one of our redundant power inputs, or both for that matter, have gone below the minimum. And we want the environmental parameters to meet Exida Profile 3, which just means that it's a field-mounted product and it has an external power supply, so it probably has some internal heating. Marketing being marketing, they insisted on doing a little bit of design on their own. So they provided us with a block diagram. Okay, it's a good starting point. So let's, oh, what happened here? They added some requirements before we even got to our own design phase. And we can see here, hey, the PC board has to be 3 inches in diameter, and bad things should not happen if the power inputs are wired with reverse polarity. Okay, we can accept that. So engineering's going to come up with a block diagram. And so we've got the power supply that takes our redundant inputs and puts out a common output. We saw marketing thought that using a 555 timer would be a good way to get our flashing lights. So we've got a 5-volt supply for that. We've got a diagnostic block for our 24-volt supplies. We've got our enunciate signal, which will initiate our flashing. So we're going to take that and put it into the ArcX tool. The ArcX tool isn't the focus of this webinar, but it's a very handy way of doing high-level failure modes and effects analysis. You can put down your blocks from your block diagram, and for many of these blocks, there is expert knowledge available, which will pre-populate your deviations for that type of block and also provide you with sample mitigations to address those deviations. Most frequently, it will provide you with multiple mitigations for each deviation, so you can pick and choose. When you're done, you're going to have a failure modes and effects analysis that you can present back to marketing and present at your design review. Not only that, your deviations and mitigations can be imported into the FMEDAx portion of the tool and used as the basis for your functional failure modes. So we got done with our design, we got done with our failure modes and effects analysis, and we drew up a schematic. So you can see the redundant inputs on your left and the common 24-volt supply, your diagnostics, your input for the flashing. Now, one interesting thing was that during the design review, it was felt that the 5-volt supply should also have diagnostics. The designer took care of that by getting rid of the 5-volt supply so that it wouldn't require diagnostics. The designer did that by replacing the 555 with an op-amp-based multivibrator. So you can see there are 2 strings of LEDs, which get divided into 4 displays pointing in various directions. It's designed with constant current sources so that as your 24 volts varies, the intensity of the lights remains the same. So here's the screen for the FMEDA tool. Oops. So you can see the database is typically pre-selected, but you can select an alternate one. And you enter your FMEDA worksheet here, and then you basically go through your schematic component by component. You add each component, you add your designator and the function of the component. Optionally, you can add which subsystem it's part of. Note that as soon as you select a component, you get the functional failures for that type of component. Here we've got an LED and we've got short circuit, open circuit, and reduced light intensity. For each of those, you can choose from a functional failure mode from a drop-down list. In this particular case, the functional failure mode, which got imported from ArcX, is lights stuck off, which is bad. And in the end, when the FMEDA is done, looking at the results screen, we indeed see that the dangerous undetected failure rate is on the high side, and for those of you who are traditionalists, the safe failure rate does not qualify for SIL 2. Now, we're probably going to go with route 2H unless we use some kind of novel technology here. Maybe there's some kind of fancy schmancy new LED we want to incorporate. But regardless, as I said, for the traditionalists, the safe failure fraction is too low. So we submitted this FMEDA and the schematic for review and pointed out that it doesn't meet SIL 2. Couple of action items for RPC. Hey, that's me. Says, change the flasher input terminal block to a 2-pin to reduce the dangerous undetected failure rate. It turned out that it was possible that there was a short circuit from the power pin to the input pin that would prevent it from working properly. And another action item was for RPC, hey, that's me, to investigate adding an additional LED string to improve the metrics. So, taking the input of the FMEDA review under review, we create a new block diagram and a new schematic. And you can see that the screw terminals now only have 2 screws instead of 3, except for this one, which of course you need 3 because you've got 2 power inputs and a common. You can also see that there's an additional string of LEDs and a constant current source for those. This makes the annunciator brighter overall. It also means that the LED arrays can face in 6 directions instead of 4, so the illumination is going to be more even around the product. Now, when we repeat the FMEDAx analysis, we find that the dangerous undetected failure rate drops by about a factor of 4. And again, for the traditionalists among us, the safe failure fraction is well up in the 80s, which is almost getting us on the way to having a SIL 3 if you want to use that as one of your metrics. As I said previously, we're probably going to go for route 2H, so we don't need to worry about that metric, but there it is for those of you who are interested. Now, meanwhile, back in marketing, managers are changing the spec. So here we go. They say there's a new spec, and they say, oh, when one more LEDs in a string fails, we should send out a diagnostic. Well, given the changes we just made by adding the 3rd string, We, the engineers, are kind of wondering, do we really need the diagnostics? Is this really the point? So we, the engineers, had a meeting with marketing and said, what do you really want here? And it turns out what they really want is that if one LED is lost, and even if an entire string is lost, that the light output shouldn't go below 500 lumens. We, the engineers, pointed out to them that this design starts at 750 lumens. So even if you lose an entire string, you're going to meet the requirements. Faced with that, they decided to change the spec to say that even in the event of an open or shorted LED, the light output shouldn't drop below 500 lumens. Based on that, the device meets the requirements and the design is approved for production. Happy ending. For those of you who are original equipment manufacturers, OEMs, our OEMX tool suite is available to you. Exida is also available to you to facilitate complex system architecture reviews that include hardware, firmware, software, ASICs, FPGAs, dependent failure analysis, cybersecurity threats. Exida stands ready to provide not just the tools, but in the event you would rather have the analysis performed elsewhere, we can provide FMEDA analysis services to provide the metrics that you need for certification and for your end users. Conclusions? Well, the FMEDA technique is a very good choice to use for failure metric generation. The OEMX tool suite is an excellent way of implementing FMEDAx. FMEDA analysis it incorporates Exida's calibrated component reliability database, which we feel is the most applicable for industrial applications. The tool is available for purchase, or Exida can take your design and complete the analysis from your schematic, bill of material, and list of automatic diagnostics. Thank you for your time. For further information, you can email me. The address is right up there on the screen, or you can contact Exida via any of the ways shown on this screen. Thanks again, and have a good morning, afternoon, or evening. Goodbye.